Before we discuss the components of the Rankine cycle, let's consider the TS diagram for a substance that changes phase. Throughout this section, we will assume that the working fluid for the Rankine cycle is water. The liquid and vapor phases of water are separated on the TS diagram with the vapor dome. The top of the vapor dome is called the critical point. At this point, the saturated liquid state and saturated vapor state are identical. If you were to increase the temperature of the water from the liquid state to the vapor state at constant pressure, the process would follow a path similar to the constant pressure line shown. Water is in the liquid phase to the left, and the superheated vapor to the right of the dome. But what about its phase under the dome? Under the vapor dome is where both saturated vapor and saturated liquid exist simultaneously. The percentage of each is determined by a property known as quality. Quality, denoted by the variable x, is the ratio of the mass of the vapor to the total mass of the saturated liquid and vapor mixture. The quality of the water when it is the saturated liquid is 0, or 0%. When the water reaches the saturated vapor state, its quality is 1, or 100%. When the quality of the steam is 100%, and it is at a higher temperature than the vapor dome, the steam is defined as superheated. When a state point is under the dome, we must know the quality at that point in order to determine the other properties like enthalpy and entropy. We will talk more about quality and see how it is used in the turbine section of the Rankine cycle. Notice that the temperature does not change when we convert saturated liquid to saturated vapor by an ideal process. The heat energy required to complete this process is called the latent heat of vaporization. The ideal Rankine cycle consists of the following 4 processes: isentropic compression in a pump, heat addition at constant pressure in a boiler, isentropic expansion in a turbine, and heat rejection at constant pressure in a condenser. The pump raises the pressure of the saturated water at point 1 to the operating pressure of the boiler at point 2. The temperature of the water increases somewhat due to the slight decrease in the specific volume of the water during the compression process. This small temperature increase is greatly exaggerated for clarity on the TS diagram. When we apply the first law of thermodynamics to the pump, we find that the work input required is equal to the change in enthalpy between the 2 state points. In the actual process, the required work input is greater due to the irreversibilities in the pump. The adiabatic efficiency of the pump can be measured by the ratio of the isentropic work input to the actual work input. Water enters the boiler as a compressed liquid at state 2 and leaves as a superheated vapor at state 3. The boiler is a large heat exchanger. The heat source can be a nuclear reactor, hot exhaust from a gas turbine, oil, natural gas, a coal fire, or other sources. The heat added in the boiler is measured by the change in enthalpy between the 2 state points. These enthalpy values are provided in the steam tables. In the actual process, there is a pressure drop in the boiler. Therefore, for a given heat input, the temperature at state 3 is lower than it would be if there were no losses. The superheated vapor enters the turbine at state point 3 where it expands and produces work. This shaft work output is used to drive other process machinery. The working fluid exits the turbine at state point 4, where it is usually in the form of a liquid-vapor mixture of high quality. If the steam quality at state 4 becomes too low, the high content of liquid in the saturated mixture can erode the blades of the turbine. The work output can be measured by the change in enthalpy between the two state points. In order to determine the enthalpy at point 4s, or at any other point under the vapor dome, we must know the quality of the mixture first. When we have determined a mixture's quality, we can determine other thermodynamic properties by this general equation. The property Y is equal to the property of the saturated liquid, plus quality times the difference in the property of the saturated liquid and saturated vapor states. The property values for the saturated liquid and vapor states, as well as the difference of that property between the two states, are all provided in the steam tables. Notice that in the actual process shown here, the steam exits the turbine as a superheated vapor at a higher temperature and pressure. Due to the irreversibilities in the turbine, some of the available energy in the steam is lost. We can measure this lost energy by the adiabatic efficiency of the turbine. The adiabatic efficiency is the ratio of the actual work output to the isentropic work output. The steam is condensed at constant pressure by a heat rejection process. This returns the steam to its liquid phase where it enters the pump. In the actual process, steam exits the turbine at a slightly higher pressure than at the ideal point 4 shown here. The pressure at point 4s and point 4a is higher to account for the pressure drop in the condenser. This increases the amount of energy rejected in the condenser. The thermal efficiency of a Rankine cycle is determined by the ratio of net work output to the heat energy input. The net work output is shown by the area enclosed in the TS diagram. The net work that is produced by the Rankine cycle is equal to the total work output from the turbine minus the work required to drive the pump. The net work of the cycle can also be expressed by the difference between the heat energy input and the heat rejected. In the actual cycle, we can see that the heat added to the system is less than ideal. Also, the amount of heat rejected is greater than we desire. This causes the thermal efficiency of the Rankine cycle to decrease. The thermal efficiency of the cycle can be increased by making sure that the average fluid temperature in the boiler is as high as possible, and the temperature in the condenser is as low as possible. This can be accomplished by superheating the steam to a higher temperature in the boiler, and by lowering the pressure in the condenser. Another way that efficiency is measured is by a parameter called heat rate. A steam turbine's heat rate reflects the amount of heat input required by the boiler to produce a unit amount of work output. A lower heat rate means the cycle can produce a unit amount of work while consuming less heat. This means a unit amount of work can be produced with less fuel, which translates to lower fuel expenses. The heat rate is inversely proportional to the thermal efficiency of the Rankine cycle, as shown in the equation. Let's go through an example of how heat rate is determined. A coal-fired power plant has a turbine generator rated at 1,000 megawatts. It uses 9,800 tons of coal per day. The coal has a heating value of 11,500 BTUs per pound. The heat rate is equal to the heat consumption divided by the power output. For this example, the heat rate is 9,391.7 BTUs per kilowatt hour. Select the thermodynamic section or the Brayton cycle.